Today I'm going to do a literature review on game theory, or specifically higher order beliefs. So the game part of game theory is usually the interesting part, and theory part of game theory is usually the boring part. So I will start with a game, and then I will go to the theory of it. Before I start the game, a lot of cell phones now have messaging applications that automatically send a read receipt when a message is read. So for example, iMessage here, it shows the time the message is delivered and the message is read, like the one here. So if we see something like this was only delivered, then we ask, did he receive my message? Or the question that most people don't ask is, did I receive his read receipt? So both are possible. So if it's like this, then I know that he read it, but do I know that he knows that I know that he read it? And the answer is no in this case, but the more important question is this piece of information really important? Or in a game, do we really need to know that my opponent knows that I know that they know the game? And the answer is yes. So now, Rubinstein's email game is the single most important example in this literature. I think some of you may know this game, but I will repeat it anyways. But I think all of you know who Rubinstein is. He's the guy who does a lot of bargaining. So the game, there are two players. To make it more interesting, Sherlock Holmes and John Watson. There are two actions, going out or staying in. I mean, going out is really going out of the house, each one of them. It's not like they go out. And the state is either good or bad, each with probability a half. So the types are, John Watson would know the state, but Sherlock Holmes doesn't know the state. So if we are in a good state, which is the table on the left, then the payoff is like if we both go out, we have good payoff. If we are in the bad state, if we both go out, we get the bad payoff. Or in any state, if there is only one person going out, then that person get a bad payoff. So the main difference of this game is basically if the weather is good, then Watson would automatically send a message to Holmes, but the message is lost with a small probability. Also, Sherlock Holmes will reply a confirmation which is like the read receipt, and this reply is lost with a small probability as well. So note that these messages, all of these messages are sent automatically, so they are not a part of action. So a player cannot choose to not send a confirmation, for example. So then the states. So the first state is the bad state, which the weather is bad. And the second state is good zero, which means it's good state, but no message is received. It basically means John Watson's initial message is lost with small probability epsilon. And similarly, good one means one message is received. So my original message is received, but the reply or the read receipt is lost with probability epsilon again. And similarly, good two means message and reply is received, but the reply of reply is lost, and so on. So the probabilities are computed very easily. And we start with the bad type. So here, when we know that it's the bad weather, then going out gives you -1, and staying in, I mean, going out gives you -1 no matter what happens with the other player, and staying in gives you 0, so staying in is the optimal strategy. And the second possibility is in Sherlock Holmes' perspective, I don't see anything. So I may think that it's the bad weather, that's why no message. Or I may think that there is a message, but it's lost. So they have probability weight 1 versus epsilon. Then if we are in the bad weather, then we get -1. If we are in good weather, then may not be 1, but the most we can get is 1. So we do the first number multiplied by -1 and the second number multiplied by 1, which gives you the expected payoff from going out, which is negative. So we still choose to stay in. And the second thing is in John Watson's perspective. So if I sent a message, but I never got a read receipt, So I don't know if my message is lost or the reply or the read receipt is lost, just like at the beginning, the iMessage stuff I talked about. So I'm actually confused with two possibilities, good zero and good one, and I assign probabilities using Bayes rule, which is a simple calculation. And then if it's good zero, I know from the previous slide that Sherlock Holmes will stay in, so that I will get -1 here for sure. And similar to the last case as well, the most I can get if we are in good one state is 1. It's not necessary that we will get this, but the most we can get is 1. So with the probability and compute again, we get a negative number, so we will still stay in. So next, in Sherlock Holmes' perspective, so I will try to explain it in what Sherlock Holmes usually do, like the power of deduction stuff. So the reasoning goes like this. So there's no reply of my reply. So either my reply is lost or John's reply of reply of reply is lost. So basically, as Sherlock Holmes, I know the state, John knows the state, but I don't know that John knows that I know the state. If he doesn't know that I know, he may think that I don't know. So I will stay in. He will stay in. So I will stay in as well. And indeed, the algebra goes exactly the same. So I will stay in. And the last one I'll do is in John's perspective. So basically, again, I know the state. Sherlock Holmes knows the state. I know that Sherlock Holmes knows, but I don't know that he knows that I know that he knows. So he may think that I don't know, so he will stay in. So I will stay in as well. So again, here goes the algebra. And you can probably reason the other cases. So let's go to the conclusion. So if we have complete information in good state, we'll have 1, 1, which is the highest possible Nash equilibrium we can get. And however, the incomplete information game, no matter how many messages are exchanged, as long as it's finite, and as long as epsilon is greater than 0, the only Nash equilibrium, or Bayesian Nash equilibrium, is both of them staying in. So the basic problem goes like, as epsilon goes to 0, as we know better about the actual state, as the information becomes more complete, the Bayesian Nash equilibrium is not continuous in the higher order belief structure, which I'll talk about a bit later. So one of the main messages is that common knowledge of the game is very different from approximate common knowledge in terms of predicting what the Nash equilibrium